For the next few discussions, we're going to start looking at the concept of potentials and relating them to the electric field and charges. But before we do that, we need to take a closer look at how to solve line integrals. More specifically, if I were to give you a field, so let's just use F for force since that gives us a lot of intuition, and a path, you'll be able to set up the integral and find out what the line integral of f dot dl is. So conceptually, what I mean is, let's say you are in the middle of you have a force field. So I think gravity is probably, since we've been dealing with gravity for a while throughout our lives, this is a pretty good analogy. Gravity is just a constant force field that's the same everywhere. And so no matter where you stand, you're going to see a force that's the mass times the gravitational constant. And so this is our vector field. And you might be given a path, say you start out here and you go up a little bit, you go down a little bit. And what you want to do is, for each of these vectors, you want to take the dot product of a short segment of length that's along this path. Take the dot product with the force. That gives you a number. Take the dot product of the next segment with the force. That gives you another number. And then same thing, you just continue all the way along through, and then you add them all up. And that's basically what a line integral is. So we're going to break this up into a few steps. I think that by itself, the steps are a bit abstract and hard to understand. So let's work through an example while we're introducing the steps. In this case, we're going to talk about a force field that is not gravity. There's some variation in it so that it's a little bit more interesting. So let's just say this person's here and is applying some kind of field of forces, and the forces take the function of this. F is equal to some constant F naught, and it's in the 4x hat plus 3y hat direction. So everywhere you're looking at in a three-dimensional space, because of this person sitting here, you're going to feel a force of F naught in this direction, in 4x plus 3y. And what we want you to do is to calculate the line integral of, we'll call this W, or force, of F dot dl along the path that's defined as y equals x squared and z equals 0. So in three-dimensional space, what that means is you have this force that's going on, so that's also taking place here, and you are moving an object along x squared, y equals x squared, and z equals 0. So y equals x squared is going to be a parabola along the x-axis, and z equals 0 is going to be on the xy plane. So you're going to move it between 2 points along this curve. In this case, the problem states that you want to go from A, which is 1, 1, 0, to B, which is 2, 4, 0. So we're going to go from 1, 1, 0, which is going to be about here, and you're going to go along this line to 2, 4, 0, which is going to be something like over there. Now, one thing to keep in mind is, in this case, I'm doing the formula for work, F dot dl, or force times distance, but which in this case, we'll talk about the concept of a conserved field later. But in this case, you don't really care what path you take. So you can go from here to here, you can go from here all the way out around the world and then back and then land here. In this case, with a conserved field, you're going to get the same result. You don't have to worry about this path issue, but that is not always the case. So while we're taking this deeper dive into line integrals, I'm going to show you the process of being able to integrate along a specific path. So just keep in mind that we're going to go through a process that's a little bit more involved, but in many cases where you're calculating the potential, it's path independent. So when it's path independent, you can just directly integrate from one point to the next without some of the steps that I'm about to introduce. But we're going to go over the complete process for completeness. So in this case, I'm in the steps, I'm going to define the field function as f, just like over here, and I'm going to define the path as some function of x, y, and z. So the first thing you want to do is just make sure you have all the components needed to write out f.dl. So in this case, we already know that our f, it looks like f naught 4x plus 3y, and we still need to find out what dl is. So that's what the next few steps involve. So after that, you want to write out the unit length. Write unit length in all dimensions. What I mean specifically is depending on your coordinate system. So dl is going to be equal to dx x hat plus, so a line segment plus the unit vector in that direction, dz z hat. In the case of cylindrical coordinates, we have d rho rho hat plus d phi phi hat, right? Nope, what do you have to add? The radius, right? So that because whenever you have a segment angle, you have to multiply it by the radius, so that's actually a unit length. And dz z hat. Hopefully once you write it a few times, you will never write d phi without thinking of putting in rho or r sine theta. Speaking of which, spherical coordinates, dr r hat plus d theta theta hat. Remember, when you're doing angle theta, you have to multiply by the radius, which is r, and then d phi phi hat. So we have to multiply by the radius, rho, and rho in spherical coordinates is r sine theta. So depending on your coordinate system, write out your full dl. In this case, we're in Cartesian coordinates. So dl is going to be equal to dx x hat plus dy y hat plus dz z hat. The next step is you want to differentiate your path, g of x, y, z, to get dx, dy, dz relations. What I mean is you take the functions that form this path that you're trying to integrate against, whatever coordinate system it is, in this case I'm just writing it out as Cartesian, but you want to differentiate it. And the key thing that you want is you want some relationships between your different unit lengths of dx, dy, dz, or dr, d theta, d phi. And that kind of ties into, let's just introduce step 4 and we'll do both at the same time. But relate in this case, Cartesian, we'll just stick with Cartesian example, dx, dy, dz to each other. So the goal is you want to get one variable that you can integrate. So let's do that in this example. So if we differentiate it here, now let's differentiate our path. So in our path, we have y equals x squared, which means that if we take the derivative, dy is going to be equal to 2x dx, and then dz is going to be equal to 0 because z is equal to 0. So now you have this relationship, which means that if you plug this into dl, the goal is now you have these relationships. You can plug them into your dl with the end goal of making it so that you only have one variable to integrate, because you only have one integral to deal with, right? So since you only have one integral and one variable, when you're integrating along a path, you should be able to define that dl in terms of a single variable by using the equations that describe the blue line, the path that you're integrating. So let's substitute these in. So your new dl is going to be equal to dx x hat plus 2x dx y hat plus 0 z hat. So now you see when I plug this into my f.dl, the only thing that I have left that's a differentiation for me to integrate is x. So that's what we're shooting for. The next step, step 5, is to sub into dl. So I guess we did that already. And step 6 is plug dl in to our f.dl and integrate. And then after that, have a drink, celebrate. So let's wrap up this problem. We have our f.dl. So f.dl is going to be equal to, f is a vector and L is a vector, technically. We're going to have f naught 4x hat plus 3y hat dot product with dx x hat plus 2x dx y hat. So when you're taking the dot products, you don't have to worry about x dot x is going to be 1. So you have 4 times dx. And then y dot x is going to be 0. Well, x dot y is going to be 0, so you don't worry about that. Y dot x is going to be 0, so you don't worry about that. So then you also have 3y dot 2x dx, and the y dot y is going to give you 1. So you only have to worry about this times this, and that times that. And we're also integrating, since this is all in terms of x, we just have to write out the x-coordinate of the beginning and end point. In this case, we're going from a to b, so we're going from 1 to 2. Now let's open up this dot product. We're left with f naught, and then 4 times dx is going to be 4. I'm going to just pull the dx out, 4 dx, and then 3.2x dx. So, and y dot y is going to be equal to 1. The dx I'm going to pull out, so I have 3 times 2x is going to be 4 plus 6x, and then I'm integrating with respect to x from 1 to 2. So now we are in more familiar territory. We just have to take this integral to get f naught 4x plus, and then the integration of 6x is going to give you 3x squared evaluated from 1 to 2. And if you plug in those numbers, you're going to get 13 f naught. So that is the line integral for f.dl along this path from point A to point B as listed here. So to summarize, well, the main concept that you want to do when you're taking a line integral is that you're often given a particular path, which may or may not matter. If it's a conservative field, then all you have to do is just integrate the start and end points. But in this case, we're just going to integrate along the path properly so that if you have to do it along a path in the future, you know how to do so. Conceptually, what you're doing is you're taking little segments of the path and taking the dot product with the field in question and then adding them all up. So we start by writing out f.dl, and the key thing is that we write out the dl based on the coordinate system, and we differentiate all the relevant equations that define the path. That allows us to relate, in the case of Cartesian, our dx, dy, dz to each other, and you want to substitute your way through so that you only have one variable to worry about. Once you get to that point where you have dl with only one variable, which is what we have here, you plug it into your integral of f.dl, open up the dot product, and then you are left with a single variable integral. So this kind of follows a trend in terms of things that you like. I like volume integrals the most, and then it just gets harder and harder, right? Surface integrals, you have to worry about which two variables and which one's a normal vector. Line integral, there's this path thing that might come in. So in general, you want to cheer to have more integrals to try to solve. In this case, hopefully with these steps, you're able to conquer any line integral that comes your way.